Have you ever wondered how we can see something that's totally invisible? Something that might be miles away, hidden by darkness, thick fog, or even solid clouds? Well, the answer is an amazing piece of technology called radar. And today, we're going to break down exactly how it turns invisible waves into a crystal clear picture of the world around us. To really get this, I want you to picture something. You're on the coast. It is pitch black. The fog is so dense you can barely see your own hands in front of your face. You have no idea what's out there on the water. You are, for all intents and purposes, completely blind. So what do you do from that position of being totally cut off? How do you find out what's actually there? The answer isn't about straining your eyes harder. It's about using a whole different kind of sense. And that sense is radar. The name itself is actually the perfect clue: radio, detection, and ranging. You see, unlike our eyes, which just passively take in light that's already there, radar is an active system. It basically shouts a pulse of invisible radio waves out into the dark, and then it listens very, very carefully for the faint echo that comes bouncing back. So let's start with the real basics. How does this whole invisible echo thing even work? Well, it all comes down to the physics of waves. And these waves act a lot like light and sound. They're just in a part of the spectrum that our bodies can't naturally pick up. The radio part of radar means we're talking about radio waves. These are a form of electromagnetic energy, just like the light we see from a lamp. And here's the absolute key to everything. We know exactly how fast they travel. They move at the speed of light, a constant, unchanging, and incredibly high speed. That fact is the secret that unlocks the whole system. The entire process really boils down to this simple four-step dance. First, the radar blasts out a short, powerful pulse of energy. That pulse travels out until, bam, it hits something, let's say an airplane. Then, a tiny little bit of that energy bounces off the plane and reflects back toward the radar. And finally, the system, which is now in listening mode, picks up that incredibly faint echo. It's that simple. Transmit, hit, reflect, detect. Okay, so now let's actually follow one of these pulses on its journey. We're going to trace it from the second it's born inside the machine all the way out into the sky to the moment it hits a target and then follows that long path all the way back home. It's this incredible round trip that happens in literally microseconds. So where does this pulse even come from? Its journey starts inside a device called a magnetron. This thing is the heart of the radar. Think of it like a microwave oven on absolute steroids. It uses super strong magnetic fields to create these incredibly powerful but very short bursts of microwave energy. The invention of this device back in World War II was a total game changer. It's what made high-resolution radar possible. Now, you can't just blast that powerful pulse out in all directions. That would be a huge waste of energy. So the radar antenna acts just like the reflector in a spotlight. It gathers up all that energy and focuses it into a tight, narrow beam. This lets the radar not only pinpoint a target's direction, but also concentrate enough power to get a usable echo back from far away. All right, so our little echo has made its long journey all the way back to the antenna. But right now, it's just a tiny blip of energy. It's basically meaningless data. The real magic happens when we decode it. How does the system turn that faint signal into useful information, like how far away something is and how fast it's going? The first and most important piece of the puzzle is distance, and radar figures this out by doing something brilliantly simple. It starts a super precise stopwatch the exact instant the pulse leaves, and it stops the watch the exact instant the echo returns. It's all about timing that round trip. This is the ranging in radar. So let's walk through a really quick example. Let's say the system's stopwatch measures a delay of 100 microseconds. Okay, we know radio waves travel at the speed of light, which is about 300,000 kilometers per second. So, a quick calculation tells us the pulse traveled a total of 30,000 meters. But wait, remember, that was the round trip, out and back. So you gotta do the crucial last step, divide by 2. And boom, the target is 15 kilometers away. Okay, so that's distance. But what about speed? For that, radar uses this really clever principle that you've probably experienced yourself, the Doppler effect. It's why an ambulance siren sounds higher pitched as it's coming towards you and lower pitched as it drives away. The exact same thing happens to radio waves. If an object is moving towards the radar, the returning waves get squished together, making the frequency higher. If it's moving away, the waves get stretched out, making the frequency lower. And by measuring that tiny shift in frequency, a radar can calculate an object's speed with incredible accuracy. This is exactly how a police radar gun works. It's how weather radar can actually see the speed of wind swirling inside a storm. And really importantly for air traffic control, it's how radar systems filter out all the stationary ground clutter, mountains, buildings, to show only the moving planes. So we've got the fundamentals, distance and speed, but modern radar systems go way, way beyond that. So let's take a look at some of the incredible engineering that overcame massive physical challenges to get us to the super precise systems we have today. This is probably the single biggest headache for any radar engineer. That returning echo is unbelievably faint. I mean, the pulse starts out as this massive blast of energy, but by the time it travels all the way out, bounces off a small target, and travels all the way back, what the antenna actually receives is just the faintest whisper. And when I say faint, I mean it. The physics here are absolutely brutal. The strength of that returning echo gets weaker by the fourth power of the range. This is a core part of the radar range equation, and it is a punishing, unforgiving law of physics. So what does that actually look like in the real world? Well, check this out. Let's say you have a target 10 kilometers away, and the echo you get back has a strength of, let's call it, 1 unit. Now, if you move that same target to 20 kilometers, you've only doubled the distance. The echo strength doesn't get cut in half. No way. It becomes 16 times weaker. It drops to 1/16 of its original strength. This is exactly why radar receivers have to be some of the most sensitive electronics on the planet. Another huge leap forward happened with the antennas themselves. We all have that classic image of a big radar dish physically spinning around, right? That's a mechanical antenna. But today, the most advanced systems use something called a phased array. These are flat, stationary panels with hundreds of tiny transmitters. And by digitally controlling the timing to each one, they can steer the radar beam almost instantly, anywhere they want, with zero moving parts. It's like the difference between having to turn your whole head to look at something versus just shifting your eyes. All right, one last clever challenge engineers had to solve. They were facing this fundamental trade-off. See, to get a really sharp, detailed, high-resolution image, you need to use a very short pulse. But to detect a target really far away, you need to pump a lot of energy out, which means you need a long pulse. So you were stuck. You could have a high resolution, or you could have long range, but you couldn't have both. Or could you? The solution is this brilliant bit of signal processing called pulse compression. It's a way to get the best of both worlds. The radar sends out a long pulse packed with energy for long range, but it's a special pulse called a chirp, where the frequency changes from beginning to end. Then, when that long, smeared-out echo comes back, a computer digitally processes it and squeezes all that energy down into one single, sharp, high-resolution peak. It's an amazing trick. So when you put all of this together, the timing, the Doppler effect, the extreme sensitivity, all this advanced processing, you start to realize that radar isn't just some machine that finds things in the sky. It's something much more fundamental. Radar is not just detection. It is the measurement of space through time. Every single one of those blips on the screen is actually a story about time. The time it took for an invisible wave to make a round trip. It's a system that builds a map of the physical world by translating tiny fractions of a second into kilometers. This whole journey began with a simple problem: how to see through fog and darkness. And it just makes you wonder, as our technology for sending and receiving these kinds of signals gets even better, what other invisible things are all around us, just waiting for us to figure out the right kind of echo to make them visible? What else can we learn to see?